Hello everyone, welcome to the course PH8151 Engineering Physics. We are discussing Unit 5 Module 3. I am R. Swarnalakshmi, Assistant Professor in Physics, Government College of Engineering, Tanjavur. Unit 5 Crystal Physics. Under Module 3, we will discuss the diamond structure and its importance, the crystal imperfections such as line defects, point defects, the Burgers vector, stacking faults, the role of imperfection in plastic deformation. At the end of this lecture, a student must be able to discuss the properties of diamond, to draw and explain the diamond structure, to calculate the atomic packing factor of diamond structure, and to compare the diamond and graphite. Diamond is known to all of us as a precious stone, and it is used in ornament making when it is of considerably bigger size. Diamond is an allotrope of carbon. We all know that in our earth, the biosphere is composed of hydrocarbons, and all dead plants and animals form fossil fuels. And when these fossil fuels are subjected to lot of pressure and temperature variation for millions of years, there are stages of transformation where coal and petroleum are formed at one stage, and when it crosses billions of years, diamond is formed. Because of such a long duration of formation, it is endowed with interesting physical properties which makes it attractive for many industrial applications as well. Diamond has a very low electrical conductivity. This can be attributed to the fact that carbon in diamond is sp3 hybridized and forms a stable octet structure because it bonds with 4 other carbon atoms in a tetrahedral fashion with a bond angle of 109 degree, 30 minutes. Because of the stable octet structure, there are no free electrons, and the interatomic bonding is quite strong. Hence, diamond has a very high melting point of the order of 3550 degrees centigrade. This makes it a good thermal conductor. So diamond is used for cutting and grinding material in industrial processes. Diamond is the hardest known material. This again can be attributed to the strong interatomic bonding. It is used as indenter in the form of pyramids or cones in hardness tests of materials. Diamond is transparent to visible and infrared spectrum of electromagnetic radiation. It has a high index of refraction. Hence, large crystals appear lustrous and are used in ornaments. It is the crystal structure of diamond that endows it with such interesting physical properties. So let us take a look into the crystal structure of diamond. It is very important to discuss the crystal structure of diamond because it is the unique crystal structure that gives the distinguishing physical properties to diamond. The diamond structure is unique as the unit cell is composed of two intersecting FCC lattices. An FCC lattice is face-centered cubic structure where there are 8 corner atoms and 6 face-centered atoms. You can see here, this is an FCC lattice. A diamond structure differs from FCC lattice in that there are additional 4 atoms due to a second intersecting lattice which is having, it's one of the corner atoms. There is a second intersecting FCC lattice with one of the atoms lying at 1/4 the diagonal length. That is, if we choose this atom to be at 0, 0, 0, then the atom of the second intersecting lattice is at 1/4, 1/4, 1/4. When you see the projection of a face-centered cubic lattice alone, that is, seeing a projection is like shining a torch onto a crystal and getting the image projected on a plane. An FCC lattice will have a two-dimensional projection like this, whereas a diamond lattice will have 4 additional atoms due to the intersecting second FCC lattice. This is a unique structure for diamond, and one another material that exhibits this diamond structure is zinc blende. Is it an yes? Only difference is that in diamond all the atoms are carbon. Here, to distinguish the second intersecting lattice, I have marked it as green. Otherwise all signify carbon atoms. Whereas in case of Z and S, these will denote sulfur atoms. Whereas the parent FCC or the original FCC will denote the zinc atoms. The bonding, as I told you, the in diamond carbon is sp3 hybridized. It will have a bond angle of 109.5 degree or 109 degree 30 minutes approximately. So here if you look, it's going to form 3 bonds. So the diamond structure bonding will look like this. Here I have shown a 3-dimensional picture in 2 dimensions, so it looks clumsy. In actual, you will have like this. carbon atom is tetrahedrally bonded. Okay. Let us now proceed with deriving the atomic packing factor for diamond. We have seen that carbon in diamond is sp3 hybridized and it has a tetrahedral structure as shown here. So one carbon atom bonds with four other. The fourth atom lies in the face centered of the left face of the cube. So, and also we saw that the carbon atom of the intersecting second FCC lattice lies at a distance of 1/4 the diagonal length. So what is the diagonal length of a cube of side A? Any cube of side A will have a face diagonal length of √2a, because by Pythagoras theorem, opposite side square plus adjacent side square equal to hypotenuse square. So here a square plus a square should be 2a square, which means the hypotenuse is √2a. To find the diagonal length, you have √2a. So the body diagonal will be, this is √2a, this is face diagonal. The body diagonal will be √3a, because face diagonal, this forms a right angle triangle, face diagonal square plus one of the side square gives the body diagonal, that is 3a square. So √3a should be the body diagonal length. So the interatomic distance, that is the nearest neighbor distance in case of diamond, will be 1/4 the body diagonal length, that is 2r should be equal to √3/4a. Okay. So we are actually trying to calculate the atomic packing factor for a diamond structure. Okay. So just like the other crystal structures, here we will start with the expression for atomic radius in terms of the lattice parameter. Atomic radius is √3/8 a. A is the lattice parameter, the length of the side of the unit cell. Okay. The unit cell volume of unit cell will be a cube. Okay. What is the coordination number? Coordination number is the number of nearest neighbor atoms. As can be seen, since carbon is sp3 hybridized, the coordination number in case of diamond is 4. Okay. So the coordination number, that is number of nearest neighbor atoms, is 4. What is the number of atoms per unit cell? In case of FCC, you have 8 corner atoms. So the number of atoms in a unit cell. For an FCC, Each corner atom is shared by 8 adjacent unit cells. This is the contribution due to corner atoms. Okay. Each face-centered atom is shared by 2 adjacent unit cells, and hence the contribution due to the face-centered atom is given by 6 into half. Due to the intersecting lattice, there are 4 atoms situated entirely within the unit cell of a diamond. So, there are 4 atoms within the diamond unit cell. So, you will have 1 plus 3 plus 4. That is 8 atoms per unit cell. Okay. So it has more number of atoms than FCC lattice in a unit cell. So what do you expect? You expect it to be a close packed structure? No. Diamond is one of the most loosely packed structure. Let us see what the atomic packing factor is. Okay. Atomic packing factor is number of atoms per unit cell into volume of each atom divided by volume of unit cell. It gives us a numerical value of how much of the unit cell is occupied by atoms and how much of it remains empty. So the atomic packing factor says us how much volume is occupied by atoms in case of unit cell. Okay. So in case of diamond, there are 8 atoms in a unit cell. The volume of each atom is 4 by 3 pi r cube, and volume of unit cell is a cube because it's a cube of side A. Substituting r equal to root 3 by 8a, you will get 8 into 4 by 3 pi 3 by 8 into 8 root 3 a cube by a cube. A cube and a cube goes off. What will remain is this 8 and this 8 will go off. 3 and 3 goes off. You will have root 3 pi by 16, which gives you the value to be 0.34. That is only 34% of the entire volume of the unit cell is occupied by carbon atoms. The remaining is empty space. So diamond is one of the loosely packed crystal structure. And remember, in spite of the loosely packed crystal structure, it is the hardest known material on earth. This is possible because of the interatomic bonding that endows it with a stable octet structure. Since we have discussed the diamond structure, now I would like to give a consolidated view of the crystal structures discussed so far in the unit 5. First, you would have seen simple cubic structure in module 2. In a cube, if there are 8 corner atoms, then such a structure is called simple cubic structure, and example is polonium. So in case of a simple cubic structure, 2r will be equal to A, and hence atomic radius R is A by 2. Coordination number, that is the number of nearest neighbor atoms, is 6 in case of simple cubic structure. The number of atoms per unit cell is 1 because there are 8 corner atoms and each atom is shared by 8 adjacent unit cells. So 8 into 1 by 8. You get 1 as the number of atoms per unit cell. And when you calculate the atomic packing factor, that is number of atoms per unit cell into volume of an atom by volume of unit cell, you get pi by 6 or 0.52. That is 52% of a simple cube is occupied by atoms. Remaining 48% remains void. In case of body-centered cubic structure, there are 2 atoms per unit cell, 8 corner atoms. In addition, there is a body-centered atom. In addition to the 8 corner atoms, there is a body-centered atom. And atomic radius in this case is given by the body diagonal. The body diagonal is root 3a, and hence 4r will be equal to root 3a. So r is root 3a by 4. The coordination number in case of body-centered cubic cell is 8 because for the body-centered atom, all the 8 corner atoms are nearest neighbors. So the 8 is the coordination number. When you substitute the value of R and the number of atoms per unit cell to calculate the atomic packing factor, you get the answer as root 3 pi by 8, that is 0.68. 68% of a body-centered cubic crystal is occupied by atoms, whereas the remaining 32% remains vacant. In case of face-centered cubic atom, there are 8 corner atoms and 6 face-centered atoms. Each corner atom is shared by 8 adjacent unit cells, whereas each face-centered atom is shared by 2 adjacent cells. So the number of atoms per unit cell will be 4 in this case. And the coordination number here would be 12. To calculate the interatomic spacing, we will be using because there are 4 atoms along the phase diagonal, here 4r would be equal to root 2a, which means r is a by 2 root 2. And when you substitute the number of atoms per unit cell and the value of the atomic radius for calculating atomic packing factor, you would be getting the atomic packing factor to be equal to pi by 3 root 2, which is 0.74. In case of HCP, here you will be having 3 atoms for it is hexagonal close packed structure where there is the top and bottom faces are hexagons, and within the body of the HCP you have 3 atoms. So here 2r will be equal to a, or r is a by 2. But you must also know the c by a ratio because c is the length here. Okay. So by knowing the c by a ratio, which is root of 8 by 3, we will be calculating the atomic packing factor to be almost the same as FCC. It will also be 0.74. The number of nearest neighbors will be 12 in this case also, because for each atom there are 6 atoms in its own plane 3 in the plane below and 3 in the plane above. So 12 will be the coordination number here also, and 6 is the number of atoms per unit cell would be 6, because each corner atom will be shared by 6 adjacent unit cells. There are 12 corner atoms, so the contribution due to corner atoms will be 2, and the contribution due to the face centered atoms will be 1, and there are 3 atoms within the unit cell, so the total number of atoms per unit cell would be 6. And for diamond, the total number of atoms per unit cell is maximum, it is 8, because in addition to the face centered atoms, there is a intersecting lattice contained within the unit cell, having 4 atoms within the unit cell. The coordination number is 4, making the diamond a very loosely packed structure, because the nearest neighbors is the least in case of diamond. The atomic radius, as we have seen from our discussion, it is 3 by 8a. The atomic radius is root 3 by 8a. This is because diamond is forming a tetrahedral structure. Okay. Hence, 2r will be root 3 by 4a. That is 1 by 4 times the body diagonal. And from the value of number of atoms per unit cell and the value of atomic radius, atomic packing factor is found to be equal to root 3 pi by 16, which turns out to be 0.34. A very loosely packed structure. In spite of loosely packed structure, it is the hardest known material. Hope this consolidated table will help you in having a bird's eye view on all the crystal structures that was discussed so far. Of course, you need to practice drawing the structures and practice correlating the atomic radius with the lattice constant, and in particular the HCP, you need to calculate the C by A ratio by using geometry. So practice will make perfect. So try to practice this. Since we have discussed the crystal systems in detail, there is an app called Crystal Viewer that can be installed from the Play Store. It helps us in viewing the crystal structure by choosing the lattice parameters and the angles. So I'll just illustrate for cubic structure alone, but you can try for all the previous lattices that were discussed in module 1. So here, if the structure is primitive and if you select this motif, it's going to be a simple cube. You can just rotate and see. Okay. So simple cube with 8 corner atoms, the bond length being denoted by the sticks. Okay. So now if I need a body centered cube and if I choose the same motif, you can see it looks like a simple cube, but when you rotate you can see the body centered atom. So it's along the body diagonal. Okay. So it just makes an interesting view of whatever we have studied so far. For a face centered cubic atom, and if I select the same motif, you can see that there are 8 corner atoms and 6 face centered atoms. By just swiping your hand, you can rotate the crystal structure and have a good look at how the atoms are arranged. It will give you a very good idea of the crystal structures. Now The diamond structure is also a face-centered structure, but with two interposed intersecting FCC lattice. So let me choose this motif. So you can see here, this is the diamond structure. Here the red color atoms denote the intersecting second FCC lattice, and as you can see, if this atom, the intersecting lattice has an atom located at 1/4 the diagonal length. And the last crystal structure that we have studied, the hexagonal. So this is the hexagonal close packed structure. Okay. So you can just install this app and try various combinations of motifs for various crystal structures. You can also give your input for length or angles and try out different kinds of crystal structures that are possible. Let us consider another allotrope of carbon, the graphite. In graphite, carbon atom is sp2 hybridized, which means it forms a planar structure with a bond angle of 120 degree and a bond length of 1.42 angstrom units. So each carbon atom bonds with 3 other carbon atoms. The 4th electron remains delocalized, and in graphite, hexagonal 2-dimensional pattern is formed by the carbon atoms. There are 1 delocalized electron. There is 1 delocalized electron for every carbon atom, and these delocalized electrons form a weak van der Waals bond between sheets. Note that the interplanar spacing is 3.4 angstrom between the sheets. Hence, graphite is very soft and the delocalized electrons account for the good conductivity of graphite. Another point to be noted is both diamond and graphite are allotropes of carbon, but diamond is an insulator. It is the hardest known material on earth, whereas graphite is a conductor and it is very soft. This difference arises because of the variation in the interatomic bonding. In diamond, carbon is sp3 hybridized. It forms a tetrahedral structure. Covalent bonding with 4 other carbon atoms results in a stable octet pattern that endows it with maximum hardness. Whereas in graphite, which is sp2 hybridized, it forms sheets which are bonded together by weak van der Waals bonding due to the delocalized electrons, and hence graphite is very soft and is also a good conductor. You can have a feel of the softness of graphite by looking at your pencil. The force of your hand is just enough to deposit graphite on the paper. So graphite is very soft. This is how nature manifests itself in different forms by various patterns of interatomic bonding. With that appreciation, we will wind up today's lecture. Let us recall whatever has been done in today's lecture. We started off with the properties of diamond. The physical properties are endowed by the unique structure of diamond. Diamond is a very good thermal conductor, a very poor electrical conductor, or in other words, it's an insulator. It has high refractive index. It is transparent to visible and infrared light. It is polycrystalline and hence it glitters in ornaments. All these properties are attributed to the unique crystal structure which we saw in detail. From the crystal structure, we calculated the atomic radius in terms of the lattice parameter. We found the coordination number to be 4. We found the number of atoms in a unit cell of diamond to be 8. Because of the two intersecting FCC lattices, which is unique to the diamond structure. From these values, we calculated the atomic packing factor to be 0.34, which implies that only 34% of the diamond structure is occupied by atoms while the rest is vacuum. In spite of such a loosely packed structure, diamond shows very large values of hardness and a melting point of 3550 degrees centigrade. This can be attributed to the strong covalent bond due to the sp3 hybridization forming octet structure. Then we compared the structure of graphite with that of diamond and the variation in their physical properties due to their structures. Hope you benefited out of this lecture. We will continue with crystal imperfections in our next lecture. Thank you for your attention.